Hi, everyone, and welcome to the fourth and final lesson in this module. And this is going to be our brief discussion on kinetics. So kinetics is the study of the rate of a reaction. And so that's basically how fast it will go. So we can think about rate as the change in concentration of reactants over time. So there are different measurements that you can take for concentration changes, depending on what phase you're in. For gases, you can measure change in volume. You could measure change in pressure. For solutions, you can measure color change with a spectrophotometer, or you can look at a change in concentration. For solids, you can measure a change in mass. Now, there are different factors that affect the rate of reaction. The collision theory states that the rate depends on the collisions of particles. That's why you stir a reaction, because you increase the number of collisions to hasten the reaction. We can also increase the rate by increasing the exposed surface area by breaking up a solid. So if you have a hunk versus granules, the granules are going to react faster, and therefore you'll increase your rate. You can increase the concentration of solutes so there are more particles. If there are more particles, there will be more collisions, and therefore your rate will increase. You can increase the reactivity of the reactants. You can increase the temperature, which will increase the number of collisions. They'll be moving faster, and therefore they will collide more. But it is important to note that collisions alone do not cause reactions. They also have to have the proper orientation and enough energy to break and allow for rearrangement to form new bonds. Okay, so not only do they have to hit in the correct orientation in order for the reaction to occur. If they're moving too slow, if they're moving too fast, if they have too much energy, it won't work. Okay, so that's why in general, we just say the more collisions, the more reactions, because the more collisions, the more likelihood there are that the proper collisions will occur. So we talked a little bit about activation energy before. Activation energy is the minimum energy required for a reaction to occur. We all know what a catalyst is. A catalyst is a substance that speeds up the rate of the reaction, and it does this by lowering the activation energy. So if we were to look at our enthalpy diagrams again, reactants, products, this would be endothermic. This would be exothermic. And again, this portion would be the E sub A, which is the activation energy, the energy of activation. Now, if I was to put a catalyst in there, what the catalyst does is it speeds up the rate of the reaction because it lowers your activation energy. So my activation energy would now be there. And so you could see less energy is required, and therefore it will occur faster. The activated complex is the high energy arrangement of reactants where bonds are broken and elements have rearranged and they are ready to bond. The activated complex occurs at the very top of that. Okay, they have a lot of potential energy. They're ready to bond, and when they do bond, the energy goes down, and so that's why the curve starts going down. So that's the activated complex. And then there we go, we see, and then we know that this one is delta H is negative, delta H is positive. So there are your enthalpy diagrams. Straightforward stuff there. Now the big takeaway is to determine our rate law. So a differential rate law shows how rate depends upon the concentration of the reactants. In a general equation, where the lowercase ones are the coefficients and the uppercase ones are the reactants and products, the rate law expression is rate is equal to K, which is the rate constant, times the concentration of A raised to the M, concentration of B raised to the N, where M and N are rate orders. Okay. So K is the rate constant. M and N are the rate orders. So what are our rate orders? We have 0, first, and second order. If something is 0 order, it occurs when the concentration and rate have nothing to do with each other. For example, if the concentration doubles, the rate stays the same. They are unrelated to each other. First order occurs when the concentration and rate are directly proportional to each other. For example, if the concentration doubles, the rate doubles. If the concentration is cut in half, the rate's cut in half. So they're related like that. And finally, second order occurs when the concentration and rate are exponentially proportional. For example, concentration doubles, rate quadruples. Concentration triples, rate goes up by 9. Okay, so they're exponentially related. So 0, not related, first directly, second exponentially. Now let's see how to answer these questions. And to answer these questions, and this is the last that we're doing with this, there are very specific ways to answer these questions, okay? There are 2 ways to actually solve this. There's a mathematical way, and then there is using your words. I'm going to stick with words only. I'm not going to show you how to do the math. If anyone is interested in doing the math, let me know. I will show you, but I think this will be easier for this very beginning lesson. So we're going to look at this data table full of information of initial rates and initial concentrations. And we're going to determine the order of reaction with respect to each reactant, and we must include a justification. So first off, we want to write a rate law. Okay, I can do that. Let me just do this so I have room to write my explanation. So we want to start. If I want to find the rate of A, I need to look at 2 trials, 2 experiments where B stays the same. So B stays the same in these 3 trials right here, 1, 2, and 3. Okay, because if I want to do this, I can only have one thing changing at a time, so I know where the change comes from. So I want to look at things where the concentrations double, triple, or cut in half, so the math is easy for me. And if we look at trials 1 and 3, the concentration doubles. What happens to the rate? It stays the same. So in this case, the concentration and the rate have nothing to do with each other. So that means A is 0 order. But what do I write in order to get that answer? What is my justification? And it's very specific what I need to write. And here's what I would write this. In trials 1 and 3, the concentration of B remains the same. We always want to start with that to show, okay, this is where we're starting. While the concentration of A doubles. Okay. The rate remains the same. Therefore, it is 0 order with respect to A. And that is my explanation to determine that A is 0 order. Now let's do it for B. Pause here because I'm going to erase this if you need to write that, because I need to show you. Now I need the space to do the next one. Now, if we're looking for the order, the rate order for B, I need to look at 2 trials where A remains the same. And it remains the same in 1, 4, and 5. Can't use 5 because I don't know what that rate is. So I'm going to do 1 and 4. So from 1 to 4, it stays the same. What happens to B? B doubles. What happens to the rate? Rate doubles as well. So that means B is first order. They are directly proportional to each other. So let's write the justification. In trials 1 and 4, the concentration of A remains the same, while the concentration of B doubles. the rate doubles. Therefore, it is first order with respect to B. Now that I have both my orders, I can write my rate law expression. Rate will be equal to K. Now, since A is 0 order, I'm not even going to include it in here. Concentration of B, I don't need to write a 1 because if I raise it to the 1, it's the same thing. Okay, so that's my rate law expression based on my table and my justifications. Okay, so I'm going to erase my justification so we can do the next problem. And it's great because all of these problems with kinetics that we're going to see are done exactly the same way, and they can only ask these specific questions. So if you can understand this problem and the practice problems, you should be able to do every kind of kinetics problem that we're going to see with these tables. So next, I want to calculate K. Okay, so what I do is I literally just take the information from the first trial. It doesn't matter which trial you use, and plug it in. I know my rate is 0.50 times 10 to the negative second. Those units are moles per liter times hour. That will be equal to K. And then I'm just going to use the concentration of B, which is 0.20 moles per liter. Concentration is in molarity, which is, we know, moles per liter. I'm going to divide both sides by 0.20, and my K will be equal to 0.025. And let me show you how these units work. I have moles over liters times hours, and I'm dividing it by moles per liter. When I divide fractions, I actually multiply by the reciprocal. So I keep change flip, right? So liters on the top, now moles are on the bottom. Moles cancel, liters cancel. I'm left with hours on the bottom. So my units are 1 over hours, or you can write hours inverse. Okay, and that's how you would solve for K. Determine the overall order of the reaction. I'm going to write what the answer is here. 0.025 inverse hours. The overall order of the reaction is simple. You just add up the individual rate orders. So A was 0, B was 1. So therefore, my overall rate order is going to be 0 plus 1, which equals 1. And then the last kind of question you could see, I've got that black box there. What is underneath that black box? Well, we don't know what rate is, but we know that our K is 0.025 inverse hours times the concentration of B. Okay, we were just using this equation and plugging in what we do and do not know. And so the rate, 1.50 times 10 to the negative second moles per liters times hour. And that's it. That's all we're doing with this kinetic stuff. Okay, it may be short, but these are the kinds of problems you're going to see. Now you're going to have plenty of time in between now and when we come back into class. So please make sure you do those practice problems, okay? Like I said, these are the only kinds of problems you're going to see with these kinetics, with these tables. So make sure you've got them down. And again, they're done the same way each time. If you want to go over another one at the end of class, please let me know. But that is it for this lesson and this module. Of course, please let me know if you have any questions, you need help with anything, but I will see you later.